In this lesson, we will be looking at the concepts of direct variation, inverse variation, and joint variation. Direct variation is most likely something you've seen before. It is any relationship that follows this equation. Y equals some constant A times X. The constant A is called the constant of variation. And what this really means is as your values of X increase, so do your Y's. They behave the same. They have a direct relationship. So as Y values increase, so do your X values increase. Opposite that is inverse variation. That equation looks like this. It's Y equals a constant of variation divided by X. And what happens in these situations is as Y increases, X would decrease. It also works in reverse. If X is increasing, Y would decrease. So they have kind of the opposite kind of thing going on there, which makes sense when you really look at it. For example, as this denominator gets bigger, you're dividing by a bigger number, so Y would get smaller. If you look back at direct variation, if X is getting bigger, well, this just amplifies it, and so Y is getting bigger. So keep those two forms in mind, because now we're going to move on and try to identify if relationships are direct variation, inverse variation, or neither. Remember what they inherently mean. Let's look at the first example A. X times Y equals 7. Well, if I rewrote that equation, I could write Y equals 7 divided by X. Well, which relationship is that? What happens to Y as X gets bigger? As X gets bigger, Y is going to get smaller, and that's an inverse relationship. The next example, B, is neither relationship. It turns out to be a linear relationship. It is not a direct variation equation because direct variation, your y-intercept is always 0. So those cannot be made to look the same, and so for that one, you have neither relationship. The final one, C, can be rewritten like y equals 4 times x. In that one you can see that as x gets bigger, y is also going to get bigger. So that is an example of direct variation. This next example is an important one. It's asking you to write an inverse variation equation. It says the variables x and y vary inversely, and y equals 7 when x equals 4. They want you to write an equation that relates x and y, and then you're going to find y when x equals a -2. A lot of kids get a little mixed up on these because they're not really sure what they're being asked and they feel like they're working in circles. What's happening is you're given an instance here when y equals 7 and x equals 4, and they're telling you that it varies inversely. As soon as you read that, you need to know that you're going to follow this type of an equation, the inverse variation equation. The problem is they want you to write a general one. They want you to find out what A is, that constant of variation. Well, you can find that out because they gave you 2 points in that equation. And so you just merely substitute in y is 7, and you know that x is 4. So now you just need to solve for A to get your constant of variation. Well, you can see that A would be 7 times 4, and so that's 28. But you're not done because they didn't ask you to find the constant of variation. They asked you to write an equation that relates them. The equation would be y equals that constant of variation 28 divided by x. And then they ask you a second step. Let me just circle this because this is the important part. That's what they're asking you to write. The second step then wants you just to evaluate it when x equals a -2. So in that case, you're just substituting in a -2 for y, or sorry, x. X equals 28 divided by a -2. And so now that you've substituted that in, you can just simply solve it and see that in that case, when you know that x is a -2, y must be a -14. But this is really the big part of it that you need to understand, that you're writing a general equation. Here's a practical application where you would see inverse variation. It says the number of songs that can be stored on an MP3 player varies inversely with the average size of the song. A certain MP3 player can store 2,500 songs when the average size of a song is 4 megabytes. Well, it makes sense that this is inverse variation. As the size of your songs go up, the amount of songs you can store is going down. Our first job is to write a model that gives the number of songs that will fit on an MP3 player as a function of the average song size. We're going to take this information that 2,500 songs can be stored when it's a size of 4 megabytes. And so we know it's an inverse variation relationship, so the number of songs over the constant, or equals the constant of variation divided by the size of the songs. And so let's fill in what we know. We know we can fit 2,500 songs on an MP3 player as long as they're 4 megabytes in size. Well, that tells us that our constant of variation is 10,000. So that's the number that changes everything by that amount every time. And so we can write a constant of variation equation and say that n equals 10,000, whoops, let me erase that. 10,000 divided by s. That's a generic equation. All right? And then in number B, or the second part, sorry, they say make a table showing the number of songs that will fit on the MP3 player if an average size of a song is 2, 2.5, 3, and 5 megabytes, as shown below in the picture. So we will make a table. S is the song size, and N is the number of songs that will fit on your MP3 player. And they're asking us to evaluate it for 2, 2.5, 3, and 5. And so when you fill that in to the direct variation equation that you've just come up with, over here for S, you will get numbers like 5,000 songs, 4,000 songs. When you move up to a megabyte size of 3 megabytes, you're going to be at 3,333 songs, and then finally at 2,000 songs for 5 megabytes. Here are some guided practice problems. In 1 through 3, you're deciding whether or not these equations show direct, inverse, or neither type of variation. And then 4 through 6, you're actually going to write inverse variation equations. Go ahead and pause the video now. And here are the answers for 1 through 3 and 4 through 6. Make sure for 4 through 6 that you understand that you need to actually write the inverse variation equation before you can evaluate it for x equaling 2. So the boxes or rectangles are around the important part that I'm looking for, and then it's very simple, of course, just to, once you have that equation, substitute in x equals 2. Down at the bottom here, it says checking for inverse variation. So the general equation for inverse variation is this y equals a divided by x. And so you could rewrite this by multiplying both sides by x as x times y equals a. So if this tells you that if you take a pair of data points x, y, and multiply them together, if you constantly take a bunch of them and always get that same number a back out, you can then say you must have a constant of variation there for inverse variation. So let's practice this on the next slide. So we have some data here, and we're going to check and see if the data is varying inversely. That's how people can tell in real life if you have an inverse relationship. This one's about computer chips. It says the table compares the area A in square millimeters of a computer chip with the number C of chips that can be obtained from a silicone wafer. And there's actually a picture of it in his hand, so that's how big it is. Our first job is to write a model that gives C as a function of A. And so C as a function of A needs to be proven to see if there's direct variation first. So what we're going to do is we're going to take all of our data points, and we can assume that we're going to have C over some constant of variation with our ginormous capital A for the area of the chip. And so if this was truly inverse variation, we could take C times A and see if we get a constant of variation out of that. Are we always changing approximately by the same amount? So let's take in our data points. Our first one was an area of 58, and the number of chips was 448. And you multiply that, and you should get about 25,984. Well, I'm going to continue to write down the data table, multiplying my x and y values together, my coordinate pairs. And you can see, as I write it down for you, that your numbers aren't too far different than each other every time I do this. Finally, I get 26,320. So you look at this whole table, they are pretty close to each other considering how large those numbers are. And so we could approximate our constant of variation to be about 26,000. And so putting this back into our direct variation equation, we would say that the number of chips relates to 26,000 divided by the area of the wafer. And we have written our constant of variation model. The next step then asks us to predict the number of chips per wafer when the area is 81 square millimeters. And so that's just asking us to apply our equation now. And we know that C is about, I could say, 26,000, our constant of variation, over the 81. And when we divide that, we get about 34. So we would get 30, oh, I'm sorry, I misread my own handwriting. Not 34, 321, which makes more sense when you look at the data. So you'd get about 321 chips for a wafer area of 81 millimeters squared. We're going to move on then to a new term, one that you've probably not heard before, and that is joint variation. Joint variation is something that occurs when a quantity varies directly with the product of two or more other quantities. So that's the difference. So here we have the quantity Z, and it's varying jointly with X and Y. And it is direct variation, keep that in mind. Here it says P is varying jointly with Q, R, and S. These A's still stand for your constant of variation. So let's write a joint variation equation looking at example 5. It says the variable Z jointly or varies jointly with X and Y. Right there we can write our equation and say that Z equals some constant of variation, which will always be there, times X and Y. It then goes on to say that Z is negative 75 when X equals 3 and Y equals negative 5. We're supposed to write an equation. So this really isn't brand new. It very much is like what you've done before. We need to find that constant of variation, and they gave us 3 values that occur in very inversely with each other. So fill in what we know. A negative 75 will equal the constant of variation, and they tell us X is 3 and Y is a negative 5. Well, when you clean that up and end up solving for A, you see that your constant of variation is 5. But that's not writing the equation. And notice they said write the equation. That's always what I'm going to be looking for. Do you go and do this next step? If you don't, it's a problem. So we have Z equals 5, the constant of variation, times XY. So there you've written your equation for your joint variation. And then finally they add on and say, find Z now when you know what X and Y are. So I know that my equation is the constant of variation 5 times 2 times 6. And so then you get 30 times 2, and Z would be 70 because it varies constant or jointly with X and Y. Example 6 asks to write an equation for the given relationship. If you think you can do this on your own, go ahead and pause the video, otherwise we'll do it together. But all the directions are given in each of the statements. Letter A says that Y varies inversely with X. So let's write an equation for that. It's an inverse variation relationship, so you know A is going to be dividing X. As X increases, Y is decreasing. Next example tells you that Z varies jointly with X, Y, and R. Do not forget to write your constant of variation still, and X times Y times R. C says Y varies inversely with the square of X. Inverse relationship means Y equals A over some value of X, which is squared in this case. So as X gets bigger, Y is getting smaller still, but now it's the square of X in the denominator. Letter D says Z varies directly with Y and inversely with X. So think about what that will look like for 1 minute. Not literally a minute, but 5 seconds. So you know that you have Z and it's varying directly with Y. So we will put our constant variation up top, A times Y, and then X on the bottom. E says that X varies jointly with T and R and inversely with S. Well, what does that mean? X varies jointly with T and R, so as those go up, X goes up, but inversely with S. All right, below we have some guided practice problems. You know what to do. Pause the video and come back when you're ready. And here are your answers. Thanks for watching.